Hi everyone, my name is Jordan, and today we'll be talking about invertebrates as bioindicators in aquatic ecosystems. We'll begin by talking about what bioindicators are, then we'll focus on bivalves as bioindicators and dive into a little case study involving microplastics in bivalves. And then we'll go on to talk about crustaceans as bioindicators and then focus on a specific example involving ostracods. And then we'll wrap up by talking about ecological implications of bioindicators and possible future directions before summarizing this presentation. So bioindicators are organisms that help scientists understand the health and quality of an environment by reflecting the presence of pollutants or changes in said ecosystem or environment. What makes them particularly useful is their sensitivity to specific stressors like heavy metals or chemical pollutants. These stressors often affect their physiological and behavioral responses, which researchers can study to draw conclusions on the health of an ecosystem. Bioindicators act as natural monitoring systems. For example, bivalves and crustaceans accumulate contaminants in their tissues, which provides a direct measure of the pollution levels over time. Because these organisms are directly affected by their environment, they help identify trends in pollution, evaluate the effectiveness of environmental policies, and can even detect emerging threats before they become widespread issues. Focusing on bivalves as bioindicators. Bivalves such as clams, mussels, and oysters are incredibly effective bioindicators due to their unique characteristics. Their sessile or stationary lifestyle means that they are continuously exposed to conditions of their immediate surroundings. This makes them particularly well suited for localized pollution monitoring. Also, their filter feeding behavior allows them to process large volumes of water, which means they naturally ingest many contaminants present in the environment. Common pollutants found in bivalves includes heavy metals, such as lead, and then also microplastics. These contaminants accumulate in their tissues over time through a process called bioaccumulation, but we'll talk more on that later. This makes bivalves not just short-term indicators, but also valuable for understanding long-term pollution trends. What's especially significant is their limited role in enzymatic activity when it comes to metabolizing certain pollutants, like persistent organic compounds, like hydrocarbons, for example. This ensures that pollutants that they accumulate accurately reflect the contamination levels of their habitat rather than being altered internally. That's all biology bioindicators. Focusing on a case study involving microplastics in bivalves. So a fascinating study out of Qingdao, China, highlighted the critical role bivalves play in monitoring microplastic pollution. Researchers were actually able to find that 80% of bivalves sampled contain microplastics. Interestingly, sediment dwelling species like clams had higher concentrations of microplastic compared to water dwelling species such as mussels. This difference arises from specific habitats and feeding behaviors. The study emphasized how factors like regional pollution levels and seasonal variations influence microplastic loads. For example, microplastics were more prevalent in spring and summer months, likely due to increased rainfall and human activities during these seasons. What makes this case study significant is its ability to demonstrate how microplastic contamination varies not just geographically, but temporally. And by analyzing the density and the type of microplastics present in different bivalve species, researchers are able to gain insight into localized pollution levels. And then this knowledge is invaluable for the creation or development of region-specific mitigation strategies which would combat microplastic pollution. And this graph on the left here just depicts the utility of bivalves in tracking microplastic pollution trends over time. And yeah. Moving on to crustaceans as bioindicators. Crustaceans, which include crabs, lobsters, and shrimp, are incredibly versatile bioindicators thanks to their diverse habitats and unique anatomy. They are found in environments ranging from deep sea vents to coastal estuaries, making them ideal for monitoring a wide range of aquatic ecosystems. One of the key mechanisms by which they accumulate contaminants is through direct absorption. They have specialized gills designed for efficient gas exchange, but in turn, they also absorb waterborne pollutants like heavy metals. Similarly, their chitinous exoskeleton, with its large surface area, provides another point of entry for contaminants. It's more so that heavy metals are able to interact with the proteins and chitin in order to remain with the crustaceans, not that they're ingesting contaminants through the exoskeleton. That's not possible. Um, in addition to direct absorption, crustaceans are able to accumulate pollutants through dietary uptake by consuming contaminated sediments, such as heavy metals like cadmium, lead, and mercury, which are also some of the most common contaminants found within crustaceans. And by studying crustaceans, scientists are able to gain insight into both present and past ecosystem health. Uh, their ability to track a range of pollutants from heavy metals to hydrocarbons emphasizes their critical role in aquatics ecosystem monitoring and conservation efforts. So a specific example includes ostracods. Ostracods are often referred to as sea shrimp and are a fascinating class of crustaceans that serve as highly effective bioindicators. What makes ostracods unique is their bivalve-like carapace, which is not only protective but also absorbs and retains chemical pollutants from their environment. These organisms are particularly sensitive to changes in salinity, temperature, and pH, which make them reliable indicators for water quality. Uh, Furthermore, their distribution within aquatic environments can shift significantly in response to even the slightest variation in the parameters discussed prior. One remarkable feature about ostracods is their ability to preserve chemical evidence of pollutant exposure within their carapace. Unlike many bioindicators, ostracod fossilization provides researchers with a historical record of environmental conditions. This means that they can be used not only to monitor current pollution, but also reconstruct past hydrochemical changes within water quality. And this will allow them to understand long-term ecological trends. So in summary, ostracods play like a dual role in ecological monitoring. They provide immediate data on water quality and act as a window into the past as well. Moving on to ecological implications. So the use of bioindicators like bivalves and crustaceans provides critical insight into the health of aquatic ecosystems, and they are invaluable for tracking long-term ecological changes and assessing the success of environmental management and conservation strategies. So one of the primary roles bioindicators serve is helping researchers identify pollution trends, and by analyzing contaminant levels in these organisms, scientists can evaluate the effectiveness of regulatory measures and even detect emerging threats to aquatic ecosystems. For example, there was a study done that demonstrated the importance of using bivalves to gauge the success of uh, a, a marine ecosystem protective policy known as MPAs. It stands for Marine Protected Areas. The findings of the study concluded that bivalves are indeed valuable in, in order to integrate scientific research with policy measures to sustainably manage marine resources. Beyond tracking pollution, bioindicators like bivalves and crustaceans also reveal cascading effects within ecosystems. For example, declines in bivalve populations due to heavy metal toxicity can destabilize sediment and disrupt nutrient cycling. Similarly, bioaccumulation in crustaceans contributes to biomagnification, where pollutants become more concentrated up the food chain, impacting higher trophic levels, including humans. Overall, the use of bioindicators not only informs sustainable conservation strategies, but also highlights the interconnectedness of ecosystems. And by combining bioindicator research with effective policy implementation, we can better predict and mitigate ecological damage. So for future directions, although bivalves and crustaceans are already invaluable bioindicators, there are several areas where advancements can enhance their effectiveness in environmental monitoring. One key area is addressing the inconsistencies in linking specific pollutants to biological responses, which I found to be a pattern when I was reading through different types of papers. Standardized protocols and comprehensive biomonitoring databases could help establish clear correlations, and this would improve the accuracy of bioindicator studies. Another promising direction is the integration of advanced technologies, for example, using biomarkers such as genetic or proteomic indicators to provide highly precise data on how organisms respond to specific contaminants. These tools will allow us for a more detailed and actionable uh, allow for more detailed and actionable data involving specific bioresponses and uh, pollution impacts. And finally, improving collaboration between researchers, policymakers, and conservationists is essential. So integrating bioindicator studies into environmental policies can promote sustainable management practices and ensure effective conservation efforts. By advancing our understanding of the use of bioindicators, we can better safeguard aquatic ecosystems for future generations. And that brings us to the summary. So we talked about how bioindicators such as bivalves and crustaceans provide insight into aquatic ecosystems, whether it be by measuring the amount of microplastics present within bivalves or uh, the heavy metals present within crustaceans, which reflect their present ecosystem. We talked about bivalves, their sessile filter feeding behaviors, and how they reflect localized pollution. We also talked about crustaceans, which are found in diverse habitats and absorb contaminants via gills and their chitinous exoskeleton. And then we also briefly touched on ecological implications involving bioaccumulation and biomagnification, which disrupts ecosystems, and how we're able to inform conservation strategies and policy measures by using bioindicators such as bivalves and crustaceans such as the ostracods. And then future directions, we talked about how we can develop standardized protocols and leverage molecular biomarker techniques in order to find a direct link between uh, bioindicator responses and certain pollutants, which would really expand the area of bioindicators in order to create effective policies. And then lastly, I want to leave with the statement saying that bioindicators are essential tools for sustainable environmental management techniques. And yeah, that's all. Thank you all for listening. You have a great day.